Good afternoon. My name is Lieutenant KJ Casola
And my name is Lieutenant Michael Hook.
from Systems Engineering 3100, and we will be presenting our design process for a Mars sample return mission.
Throughout history, mankind has continued to explore new frontiers and expand our knowledge of the universe. To this end, several missions to Mars have already been conducted. These range from Mariner 4's first flyby in 1965 to the Opportunity's rover and Curiosity, pictured in the upper right, still operating on the Martian surface.
While probes and rovers are a good start to exploring the red planet, NASA ultimately wants to conduct manned exploration missions. In support of this, NASA desires to expand current knowledge of the planet's surface and atmosphere, and to test equipment necessary for a return from the Martian surface back to Earth.
Any new mission to Mars must start with a basic systems engineering analysis approach. This often begins with a problem description. For this Mars sample return mission, NASA desires to obtain atmospheric and surface samples representing 90% coverage geographically and geologically of the surface. This mission is to spend no more than one Martian year on the surface collecting these samples, and the mission must launch from Earth by 2024 using existing launch vehicles.
Armed with the above problem description, the design team set to work on the systems engineering process and came up with their recommended solution: a low-energy transit to Mars, deploying multiple sample vehicles from orbit to include balloons, atmospheric sample collectors, and wheeled rovers for surface sampling, and a rendezvous for pre-staged rocket ascent to dock with an orbiter for the return trip. The following slides will describe the tools the design team used to reach this solution.
The first step towards reaching this solution was to conduct a stakeholder analysis to determine effective needs of each stakeholder. The table shown represents all of the stakeholders considered for this mission. Stakeholders were broken up into major categories and further by stakeholder type. For example, NASA was the sponsor and as such was considered the client and primary user. Meanwhile, the United States government, as the financial sponsor, was considered an indirect user.
Other stakeholders considered included the technology developers, academia, the media, and the international community. For each stakeholder category, that stakeholder's needs and concerns were analyzed. Finally, stakeholders were classified as either a decision maker or an influential party, and their associated interest level evaluated.
The next step of the process was to develop operational scenarios. These non-solution specific scenarios help the stakeholder and design team visualize what is happening during the mission. This allows the design team to begin to develop a list of required functions the system must be able to perform. Vignettes are alternate or what-if scenarios that are intended to expose weaknesses in the design that could degrade the mission or cause mission failure altogether.
The following four vignettes were considered in the design: delayed launch from Earth, which resulted in adding the requirement to be able to accelerate or even decelerate to regain intended track, effectively widening the launch window. Transport ship collision with space debris, which resulted in the addition of collision detection and avoidance systems to the transporter. Possible loss of communications resulted in the decision to add redundant or secondary communication systems. And finally, the delay or failure to rendezvous on the Martian surface for relaunch back into Mars orbit. This could result in a delayed launch back to Earth or returning on time without all of the samples. It was determined Mission Control should have the ability to analyze and make this decision on the spot.
Together, the operational scenarios and vignettes were used to create the contextual diagram on the right, displaying how the transporter system should interface with its surrounding systems. These surrounding systems include the rovers, mission control, and both the space and Martian environments.
After gathering a list of required functions from the operational scenarios and contextual diagram, the next part of the process was to decompose these functions into subfunctions. The figure on the right displays the functional hierarchy used to design the Mars sample return mission.
However, a hierarchical organization does not help visualize the required sequencing of these functions. This was accomplished by organizing the functions into the below functional flow block diagram. Here, functions sequentially follow the direction of the arrows, and possible decision points or path splits are annotated with and/or operators. With the list of functional analysis complete, the next step was to list and then define all requirements necessary to successfully complete each function. This requirements definition was conducted for the following main functions: entering Mars orbit, deploying sample vehicles, collecting samples, positioning at landing sites, and rendezvousing with the orbiter for return.
Requirements were listed in table format. A typical full systems engineering project could contain hundreds to thousands of requirements. For visual purposes, a sample requirement is shown below. These requirements were broken up into a reference number, the actual requirement condition, the measure of effectiveness, the required threshold and objective values, and any related subfunctions. In any systems engineering process, there will be multiple design options. How does a design team know what all solutions are available prior to even beginning the process of filtering out the viable solutions from the not so viable solutions? The answer can be found using a morphological box. The displayed morphological box shows all of the possible design combinations, an astounding almost 584 million unique designs. These design combinations are chosen by selecting one option from each category. For example, one example solution is shown here in red boxes.
Alternative designs could be selected by making different selections in each category. Keeping in mind, making some selections suggests making certain selections in other categories. For example, choosing to use a single sample collector and choosing a sample collector that does not relocate positions is probably not going to achieve 90% coverage in any timeline, let alone one Martian year requirement. In order to determine what the best design would be, the design team developed measures of effectiveness, called MOEs, to quantitatively compare the designs side by side. These measures of effectiveness were percentage of Martian coverage, maximum acceleration of sample vehicle during landing, number of corrections made, both transiting to Mars and entering orbit, and the distance the sample vehicles land from their designated sites. The next step was to assign value curves for each of these MOEs to graphically represent how the value to overall mission changes with different levels of effectiveness.
Percentage of Martian coverage can be seen in the top left. Here it was determined that returning only a couple samples were not very useful for the cost of the mission. As sampled area grew, value increased to the point where high sample numbers really didn't add any further value. In the top right, maximum safe deceleration during landing was determined to have a certain threshold value depending on design, but values below that were determined to linearly relate to the value. Bottom right is the number of corrections required. It was determined there will be a limited amount of fuel on board, here estimated to be about enough for 25 course corrections. A couple corrections are expected and provide no value decrease, but as the correction number approaches 25, there is a steep value decrease as running out of fuel becomes a concern. Bottom left is landing distance from the sample site. Landing further from the site will cause delay, as more travel time is required. The curve looks similar to that for number of corrections, as a certain missed distance is expected. As this distance increases, there is a possibility of running out of time to transit to the assigned sample sites.
Swing weights were assigned to the MOE value curves and 8 different designs compared, as seen here. Alternative Design G had the highest overall score. Alternative Design G involved a low energy transit between Earth and Mars, used multiple atmospheric and sample soil collectors deployed from the orbiter to the surface, and utilize proven wheel-based technology. This design should meet all stakeholder needs using the most reliable design and providing the greatest coverage as determined through accepted systems engineering processes.
The systems engineering approach to design wouldn't be complete without considering testing and evaluation. Testing and evaluation provides verification and validation for the stakeholders. As an example, we'll consider the technical issue of rover mobility. The testing procedures involved would include controlled environment testing, such as in a lab or in a testing area that replicates conditions on Mars. For a real-world demonstration site, the Mojave Desert provides a great site to test things like endurance, energy efficiency, and autonomous navigation proficiency.
In conclusion, using the systems engineering process has led to the best design and is ultimately the best method for meeting the stakeholder needs.